Well, now we continue with the proof of part 3. I needed a little more room, so I had to erase the theorem, but basically here's what we're proving. We're proving that, remember that f and g are both continuous functions at x naught, and we're now going to prove that f over g is continuous at x naught. Well, we know that g of x naught is not equal to 0. So what we're going to do is initially we're going to bound the function away from 0. We're going to find a little interval around x naught where it's either completely above the x-axis, all positive, or completely below the x-axis, all negative. Okay, so bound g of x away from 0 in a neighborhood of x naught. Well, let alpha be 1/2 of the distance from the x-axis to g of x naught, just the midpoint between the x-axis and g of x naught. And then we'll make it the absolute value, so it's positive. So alpha is positive, and notice that with simple algebra, the absolute value of g of x naught is equal to 2 of alpha, or 2 alpha. And let's see, maybe I'll draw this. We're setting g of x naught, the absolute value. I might erase this in a minute, but just to get a little visual here. If that's 2 alpha, and let's say this is the origin, let me make it a little closer. Let's say this is the origin or the x-axis. That would be 0. So this would be alpha, and this would be 3 alpha. Okay, so if x naught on the x-axis is, say, right here, g of x naught is right there. G of x naught is equal to 2 alpha. The absolute value, you can just assume that g of x naught is positive. It would look the same even if it were negative because we're taking the absolute value. Let's say the function looks something like, something like that. You can draw it however you want to. Okay. Well, because we know that g is continuous at x naught, there's a delta 1 greater than 0, such that if x is in the domain and x is really close to x naught, within delta 1 of x naught, then the distance between f of x and f of x naught is less than alpha. So we've already drawn this on the board in a way, but that's possible. Or I could have said this delta 1 exists because g is continuous at x naught. Well, notice this, if this whole thing right here, we can see very clearly in the picture. Since g of x naught is 2 alpha, and what does this say? This says that the distance between g of x and g of x naught is less than alpha. Well, we're going up in heights, right? So if x values are within alpha of g of x naught, it means they're in this strip right here. That's what I'm saying here. It means that g of x is in that strip, means that the height of the function value, is between alpha and 3 alpha. So we're caught in this strip right here. So my delta 1 might look something like this. X naught plus delta 1 is right there. X naught minus delta 1 is right there. So if you're caught in this strip in between x naught and plus and minus delta, the height of the graph is less than or in between alpha and 3 alpha, because it's within a distance of alpha of this point right here, which is 2 alpha. So any questions on the picture? I think it explains it fairly well, why this is true. Okay, so this is actually what we're going to use right here in a couple of minutes. If x is close to x naught, then g of x is Yeah, this is, all I did is take off the 3 alpha part of it. All I want is for g of x to be bounded away from 0, so it's actually greater than alpha. Okay, let's finish up. See if I can leave that picture on the board without running out of room. Now, let epsilon greater than 0 be given. And I'll tell you why we're doing this. To show that 1 over g is continuous at x naught. That's what all of this previous work has been to do. I know we're going to prove f over g is continuous, but the main part of it is just going to be proving that 1 over g is continuous at x naught. Okay, since we're showing continuity, we've got our epsilon greater than 0. Now I'm going to let epsilon prime be something kind of funky. It's going to be alpha times g of x naught in absolute values times epsilon, which is obviously greater than 0 because we're multiplying 3 positive numbers together. Now notice that g of x naught in absolute values is equal to 2 alpha. I actually could have written this as 2 alpha squared, right? 2 alpha squared epsilon, but this will look more familiar as we move ahead in the next minute or two. Okay. Since g is continuous at x naught, we're going to do something similar to what we did on this line right here, but for the function g. Let me see what I did here. Yep, I've got a mistake. This less than alpha up here should be g. We're concentrating only on g right now. See if I've erroneously used f anywhere else on this so far. That looks like it. So this line is going to look almost identical to that line right there. Since g is continuous at x naught, let delta 2 greater than 0 be such that, yeah, I'm using a different delta now instead of delta 1, be such that x in the domain and x minus x naught less than delta 2 implies g of x minus g of x naught in absolute values is less than epsilon prime that we defined right here. Well, is typical when we define two different deltas, a delta 1 and a delta 2. Now I'm going to say let's delta equal the minimum of those two. So let delta equal the smaller of delta 1 and delta 2. So therefore, if x is within delta of x naught, then this is true, and this is true as well, or this right here, the thing with the star by it. It follows that I'm going to try to continue left to right here. It follows that x in the domain and x minus x naught less than delta, which means it's less than both delta 1 and delta 2, implies the following. I'll write it. I don't think I have enough room. Yeah, I guess I'll start it here. 1 over g of x minus 1 over g of x naught. And remember what this is. This is the same as writing 1 over g of x and 1 over g of x naught, taking the difference of those two. And now I'm going to rewrite that in absolute values where we have a common denominator. So the common denominator is going to be g of x times g of x naught. And what would the numerator be? If this is 1 over g of x, I had to multiply top and bottom by g of x naught minus g of x. Almost done. What do we know about that fraction? Well, what do we know about the numerator of that fraction? What do we know about g of x naught minus g of x in absolute values? Well, I know that it's less than alpha. I know that it's less than epsilon prime. And I'm going to replace that with epsilon prime on top. That numerator is less than epsilon prime. Okay, so if I want to make this bigger, right, I can either make the top bigger or the bottom smaller. So I can replace g of x, because of this, I can replace it with alpha. And g of x naught. And that is equal to, let's see, epsilon is epsilon prime over that. So that's equal to epsilon. I really have one more line to write. What we did just prove is this. We just proved that 1 over g is continuous at x naught. So, to finish this off, maybe I'm going to continue right here. Thus, 1 over g is continuous at x naught. Well, if 1 over g is continuous, f over g is 1 over g times f. Two functions that are both continuous at x naught. So therefore, and maybe I'll write the reason here. By part 2 of this theorem, f times 1 over g of x, which is f of x times 1 over g of x, is continuous at x naught. And that finishes the proof.
Is this section 3.2?